crypto game JavaFx project that we have, and basically this is to showcase how clients can talk to one another through this server that kind of acts like a hub. The server is going to be taking in encrypted messages from, let's say, Alice, and sending that same encrypted message to Bob, where Bob can be decrypting that message. Now all the encryption happens through the server generating public keys that will help with encryption, and then we do have one case of a cipher where they generate public and private keys to showcase asymmetric encryption. So another part of this app is that you can also have an attacker that joins the server, and the attacker's job is to listen into conversations or test out keys and try to figure out what the key is for the encryption. They have 4 modes and 4 separate attacks that they might have to consider with run analysis, such as frequency analysis or the commit. Okay, so just to talk about architecture a little bit, what we decided to do was kind of work with a model view controller system. So with the JavaFx project, we still have this main file that kind of runs the whole project in the beginning, but what we do have is separate into controller, model, and view. So for view, we're going to have some assets, which is basically just some icons that we use throughout the application, but also these fxml files which control the UI, like what it looks like, what buttons are there, text fields and text areas, and what else. We also have a styles.css file just to help with more styling, make the UI a little more unison. And now for model, we have a cipher class, a conversation class, message. We needed a independent RSA and RSA generator class just because the code was a little too large that we didn't want to include it with the cipher tool. And then we have this tool class too, which is meant for analyzing and structural analysis with frequencies and frequency tests and whatever. So with Cypher, you're going to find the stream encryptions, the visionaire, and the monoalphabetic. Conversation is the object that attackers usually interact with because this is what's going to hold messages between 2 clients. And this is what the attacker is going to keep checking until they beat the encryption. This is where they also understand where the key is too. Message class is the actual object that we're sending over through our client and server socket threads that we have in this JavaFX project. So basically, when a server sends to a client, they're sending it in this form, which is a message which will always have a from message, the to, the actual message itself, the type of message, if it's encrypted, if not then it's implied decrypted, and the type of cipher that was used for that specific message. And then we use constants just to keep track of the state. And then we also made it serializable for the output and input streams. And let's see. Now for controllers, this is just what we use to control each fxml file. There were a lot, but basically that is it. Test or brute force. So let's go run the application. Alright, so we're given these 3 options: server, client, attacker to start as. We should start as server. So any port number, I'm just doing 4040. We can connect, and right here, server is open for connection. And now, as a client, I want to connect that same port number. Let's do Tom. And then the same thing here, 4040, let's do Xavier. Okay, so I see Tom here, and now I want to connect to him, and we have 4 ciphers to go and choose from. I'm going to choose monoalphabetic, and what's going to do is going to send an invite to Tom, and let's go accept the invite. And now we can go talk to Xavier and Tom. So, hello, how are you? And now Tom will be getting this message from Xavier. He can interact with the message since it's encrypted and decrypt the message. So he can send a message right back. I am good. How are you? Testing some numbers. Yeah. Okay, great. Okay, so we can decrypt that. And then we can decrypt that. Okay. Okay, so let's go move on to the next ciphers. We can do same port number. Let's do Bob. And then over here, we need Jack. And now we can see that the previous two clients are still there since they're still live in the server. And then now we want to connect to Bob with the Visionaire cipher. So I'll send out the invite. We accept. And now they can talk to each other. Tell her hello. Hello world. And then we can decrypt, same thing as before. Now keep in mind, the server is going to be able to keep track of all of this since it is the hub. We can see when it opened the connection, when it got a connection from a port, added that connection as a unique ID. We got Tom over here, and then rinse and repeat. We can also see when new conversations were initiated, like Tom and Xavier are now talking, and then keep track of any generated keys and any messages coming in and out of the server. Right. Okay, and now moving on to the third cipher. Bob. Oh, we already have another Bob. Oops. Giving the unique IDs. We can do Vance. Let's connect to this Bob. And let's do stream. So let's accept the invite. And now we're going to be in another chat room. Hey, how are you? Some gibberish. And now what's different here is that we're actually getting a different format of the encryption. This is kind of like in bytecode, and then now we're going to go decrypt it. And then same thing. Okay, and now the last cipher is going to be a little different. Let me set it up. Okay, so we're going to be using the RSA cipher. And this is the only cipher that has not just a generated public key, but also a private key. So the server lets clients share each other's public keys, but they keep their private key secret. The public key is meant to encrypt your messages, but the private key is meant to decrypt messages. And this is considered asymmetric encryption. So, hi. Hello. Okay. And then let's go decrypt. And there we go. Same thing, just a longer message. And that's practically it for the client. But last thing I want to show is for clients, they can also log out of their sessions. So when they log out, they get a notification, oh, someone wants to leave the chat. And then they get back into the connection setup if they want to start up a different connection to a different server or what else. And we can do the same thing here. Let's just close up some connections. And once again, the server can keep track of all of this. It can detect any terminated type messages that they want to send. And then we can end conversations. So Nancy and Leo ended their conversation. And then we can close that socket from the
Alphabetic cipher is a substitution cipher in which the cipher alphabet for each plaintext alphabet is fixed during the encryption using a given key. For example, if A is encrypted as J, then each A in the plaintext will be encrypted to J. The first method is the generate monokey method. This method will return a string which will be the key for encryption process. First, we list out all the methods in order as a string. Then create a list called alphabet and store each character of the alphabet in it. This is so we can randomly shuffle every single character using the shuffle method. Once that is done, we create a string builder that has the same capacity as the size of the alphabet list. We store the newly shuffled alphabets into the string builder, which will be our key, and this is returned as a string using the toString method. The second method is the monoalphabetic enc method. It accepts the key and the plaintext as strings. This method will encrypt the plaintext using the key, then return the ciphertext as a string. First, we create a char array called alphabets and add all the alphabets to it in order. then initialize another char array called ciphertext that holds the plain text. Then it outputs the length of our key in this test, which will always be 26. Then output ciphertext.length, which is also the length of our plain text in this test. Now we encrypt using nested for loops. The first for loop will run as long as the ciphertext.length. This is to make sure that we only encrypt as many characters as the plain text has. The first if statement compares the character in alphabets at index A with the character in ciphertext at index X after turning each character to lowercase. But if the character in ciphertext at index X is uppercase, then character in ciphertext at index X will be set to the character in key at index A in uppercase. If the character in ciphertext at index X is lowercase, then character in ciphertext at index X will be set to the character in key at index A in lowercase. Else, ciphertext at index X will be set to the character in key at index A. This process will keep on going until the full plain text has been encrypted. Then it outputs the ciphertext and also returns the ciphertext as a string. The third method is the monoalphabetic deck. It accepts the key and the ciphertext as strings. This method will decrypt the ciphertext using the key, then return the plaintext as a string. First, we create a char array called alphabets and add all the alphabets to it in order. Then initialize another char array called plaintext that holds the ciphertext. Now we decrypt using nested for loops. The first for loop will run as long as the plaintext.length. This is to make sure that we only decrypt as many characters as the ciphertext has. Encryption and decryption are pretty much the same algorithms. The first comparison starts out between character in plaintext at index X and character in key at index A, both in lowercase. Through the if statements, the decryption process is done, and then it outputs the decrypted text and returns the plain text.
I'll be going over the methods for the Vigenère cipher, a polyalphabetical cipher based on substitution. The first method I'm going over is the encryption method, which simply takes in a key and a plain text as its parameters. It then takes that information and then encrypts the information here in the for loop. If the ASCII character for space is found, it'll put a space in between the words, otherwise it'll just encrypt it as normal. Moving on to the decryption method, this one takes a key and the message as well, and the same thing in the for loop. It will check if there's a space character. If there is, it'll skip, otherwise it'll decrypt the message as normal. Here I make use of a helper method, the decrypt counter, which is simply just a method to help me keep count and have it increment as it goes through the decryption, and then it gets added on to the ASCII characters here. The next method we have is the getInfo method, which takes in a message and a key. I use this method when creating the cipher on my end so that I could get my information and then move it over to my encryption and decryption methods. The last method is the Vigenère table method. Its only purpose was to create a table that contained the alphabet, which I used up here in my encryption method.
Alright, so this is the stream cipher that we worked on, as you can see right here. The first method we have here is the encoding. So obviously as the parameters, we're taking in the key and the plain text that we want to encode here. And we're using this exclusive OR operation that we defined down here. And we're using it on the plain text and the key, but they're byte array versions. So we're using the get bytes operator on both of them so that we can use the exclusive OR operation. And if we go into the exclusive OR operation over here that we're defining, we can see that we're taking in the first parameter as a byte array and the second parameter as a byte array. The first one being the plain text and the second one being the key.
You can see this little snippet of code right here is just in case the key is a longer length than the plain text, in which case we would just shave the length of the key down to match the length of the plain text. Afterwards, you can see that we're looping through the plain text, and we're taking each byte and we're using the exclusive OR operation, which is denoted by this character right here, and we're using the exclusive OR operation on each byte in the key. And this little snippet right here is just in case the key is a shorter length than the plain text, in which case we just make the key repeat itself. That way the length of the key can match the length of the plain text. And right here you see that we're adding a comma here, because what we're returning is not actually the ciphertext as a string, but the byte array as a string. The reason we're doing this is if we were to return the ciphertext as a string, our UI is not actually recognizing some of the characters that are being printed out, meaning that when we're trying to decipher, we can't, because we can't get the characters, because our UI just doesn't know what they are. So that way we're using a comma, and then when we're decoding it down here in this second operation, we're using the commas as delimiters so we can get each byte. So over here in decode, you can see that we're doing a pretty similar thing right here, except that we're going to have to transform this byte string array into an actual byte array. And after we do that, everything's pretty similar. We're exclusive ORing the key and the ciphertext to create the plain text, and that is what.
Okay, so for one of the ciphers, which is RSA, this is supposed to show the asymmetric encryption. So this code kind of works like with two classes. We have the RSA class and then an RSA key generated class, which I'll talk about later. Now right here, what we're really accessing from this class is these two static methods, encryption and decryption. So for encryption, it's a method that takes in the plain text and a public key, and is returning a byte array. And what it's doing, it's using a cipher library and initializing it into the correct format. Now we're getting this public key from over here. We're converting public keys with this X509 encode key spec. These are both just basically helper methods for that public and private key. And for decryption, we're simply just throwing in that plain text that we got and the base64 private key. And then we're decrypting it with base64.getDecoder.decode, and then returning the string. Moving on to RSA generator. This one's real simple. What's really going on is we're just accessing these two methods. This is what's most important, get private key and get public key, but we can only access this after we initialize it with the constructor. So we always need to make an object for the RSA generator, and every client is supposed to have their own unique RSA generator object, because that will give them their public key, which is where they can share how other clients should be encrypting their messages for them. But their private key is kept secretly for themselves. This is meant on how to properly decrypt those messages coming in.
I'm going to talk about the attacker. So the attacker needs to connect to the server. Now I'm going to put in the port number that the server is running on. 2000 in this case. Select mode of attack. So we're going to start with ciphertext only attack and connect to the server. Now that I am connected to the server, in ciphertext only attack, what happens is I'm going to query the server for some ciphertext, and then run analysis on that ciphertext to figure out the possible key, or maybe try to decrypt the ciphertext. So I'm going to go ahead and query the ciphertext, and here I have a ciphertext. So I have a few options. So if I was if this was a Vigenère cipher, I would choose the key length here and figure out, try to run analysis to find the key. But I'm just gonna run analysis and see what kind of ciphertext am I dealing with, and my analysis will tell me what to do next. So I'm gonna click analysis, and it looks like that I have a monoalphabetic. So the way I know this is because I have frequency of letters, and then I have a possible key telling me that okay, each letter is mapped to another letter. So this is shown in monoalphabetic, and this analysis allows me to analyze the ciphertext. Another option I would have is called brute force attack. Using brute force would be just trying to search every possible key, but in monoalphabetic the key space is pretty large, but it's doable, but it's going to require a lot of computational power. But in this case, I'm just going to show you a way this happens. Normally this would take a long time, but just for this demo purpose I'm going to shorten the length, but this will take a long time because of the key space. It's 26 factorial. So I would click here, and if you could see in the corner, the process has started, and I kept the key space small for the demo purpose to show that this is actually it's randomly creating a key and checking that is it possible. It's checking with the server, is this a possible key, and it's constantly checking and verifying. So for the demo purpose I kept the key space short just to see that it's actually doing the algorithm, but in the case that it actually finds the key, it will notify the attacker. But in the case it doesn't, it will just complete the algorithm and it won't even give you it won't tell the attacker anything, really anything. So in this case we didn't find anything. So now we're gonna go and disconnect and try the next mode of attack. Let's continue on to our next mode of attack. Let's retype our credentials, connecting to the server again, and let's choose non-plaintext attack and connect to the server. So in this I see that I can query the server again in known plaintext, which means I have a ciphertext and its corresponding plaintext. So server being the challenger and the attacker being the adversary, the adversary is going to query the server for this. So I'm gonna query the server. Now that I've queried the server, right, and server had stored some conversation. Now, well, in the way the system is designed is that there is two people talking right now, and then their conversation is happening, and the server is storing that conversation. And now that this attacker is trying to key into finding out what they're talking about and really trying to get the key, basically. So in known plaintext attack, the attacker has queried the server and he has received a plaintext and its corresponding ciphertext, and the attacker can make multiple queries, but there's a limit. So in this case it's going to keep querying until the it can get up to 10 messages, and in this case it will get the maximum number of messages that the server has stored. In this case I guess that's all. So that's all the server has stored, and up to 10 messages the attacker will be able to see when the server sends it. So in this case it's hello Bob, and that's the corresponding ciphertext, and that's the corresponding ciphertext for this plaintext message. Again, if I run analysis, it's basically going to analyze this and try to determine the key, and that is the simplest way this known plaintext attack works on Krypto Chat. And now we can go ahead and disconnect and try the next mode of attack. And again, like also this is configured so that if I don't have the correct credentials, this will let me know. So for example, let's say I don't put in the port number, or let's say I don't put in the port number. Will this let me know? It says please enter the port number. So it handles those exceptions really well. Completing known plaintext. Let's now move on to chosen plaintext attack. So let's again connect to the server and choose our mode of attack. Now let's connect to the server. Now that we have connected to the server, well, chosen plaintext is the attacker gets to choose what plaintext they get to encrypt, and they do not get to choose the encryption mode, but really they get to so they get access to the sort of the server as an oracle, so they can choose their own plaintext. And like here I can see, hey, hi Alice, and I want this to be encrypted. Because hey and then Alice is a common word between many conversations that might be going on between Alice and Bob, getting a decryption for this is essential. And so I can, for example, since I queried this, say I want to query something else, I can query something more common like hi Bob, right? And querying that, so hi, so right off the bat, like the attacker can know that this is monoalphabetic, and really like and then eventually, you know, having enough plaintext encrypted, and then having its ciphertext and making those comparisons, running frequency analysis on these, can really lead to finding the key. So again, let's see something more common. Bye. So as I can actually make the attacker can make many requests like that, but really that's the gist of what chosen plaintext attack is. And let's go ahead and check out chosen ciphertext attack by disconnecting here, and let's retype our credentials again, server port number, and choose our mode of attack, chosen ciphertext attack, and let's connect. And again, very similar. So the attacker gets to choose their ciphertext and see its plaintext. So for example, we saw that P was for buy, right? We saw that. So let's query and see what does P stand for. P is B. So this way, actually, the attacker can get, but they're not allowed to submit an alphabet or anything like that. But they can do single queries or single or like multiple phrases, and those are the queries that they can make. So for example, let's say the attacker wanted to know what hi was, right? And they saw that in chosen plaintext attack they put hi, and it was something similar to JK. So it's like hi, yeah, JK. So something like, so all these phrases could be ciphertext, and this is, well, monoalphabetic is very simple, and in terms of trying to guess. But if the server chose a more an advanced cipher, it would be harder for the adversary to really guess something as simple as hi and bye. So let's disconnect and So the gist of this these modes and these attacks and incorporating the server with the attacker is basically attacker can query the server and show you really that the attacker can gain control, can gain access by really decrypting these methods, but the server really decides what is being decrypted, what is happening, by really putting constraints on the attacker. And this is the Krypto Chat attacker model. Thank you.